Welcome back, guys. Last week we touched on how we can implement the file system for our own kernel. So now that we have the actual schedulers and the switching part and also MMU done, we have a baseline for our kernel, and we wanted to implement the syscalls in general, almost everything, but to even have a working user space with enough syscalls, we need some sort of file system. That's why we were starting with these stuff. So we need a file system that can allow us to implement these syscalls in general, and this is what we have been trying to understand last week. And we were reading through how exactly Linux implements inodes and how superblock works and stuff like that. So I was also looking into some articles after that over the week, and this article seemed really interesting because it just gives out how exactly in high level how exactly Linux implements this, and probably it's fact checked better than LLMs. But LLM's output seems almost perfect. I didn't find much difference between this article. Probably maybe this article was written by LLM, I'm not sure, but in general this article gives us an idea of what Linux considers as a file system. So let's just go through it and see which information is needed for us. We're not going to go through the entire article, that would take a lot of time. So I was just gonna take a look at inodes and superblock, because that's the two things that we are gonna implement in our site. And yeah, inode and superblocks. So as you can see, like in general, what is a file system? File system probably is if there is no file system, how would you consider a file? A file is just a memory with some metadata. So it has a name, it has some location, and it has some permissions, and it has the actual output, actual data of the file. So this is what we consider as a file. So if we have like a tree of files, then how are we going to manage it? How come you know that, let's say you want to read this particular file, how will you know that particular file's location in memory? If you had only in memory file system, probably you can just keep pointers to all the existing files in a hash map and look up those pointers and consider them as a file. That would work fine, because that is also a general idea of what a file system, or at least what we consider as files, and how we make files useful. Because in general there's nothing much, you just have to find files and you have permissions and you read write to those files. So having pointers to memory locations and inside a hash map and looking up things also, and within every key you can also have the permissions related to it and you can check them. That also makes sense and it's almost also fine. But we don't have a memory, and file systems are really huge, because as you know, even you might have like 1 TB 2 TB external drives, and in memory is fast, but it's not scalable because you only have a finite amount of RAM. But external disks are practically infinite, because you can just scale 2 TB 3 TB and it just scales on and on. And I also checked that Linux supports like any other what's that, cloud disks as a file system, because in general, instead of you having a physical disk, whatever you do through your command line just is getting pushed into the G Cloud or whatever cloud provider you have. So that's the thing. So if you have an in-memory system like that, it's not that scalable. But if you have a physical drive of 1 TB, 2 TB, it's scalable and you can have a lot of data in it. And inside physical devices, you can't simply have a hash map because they are just physical things. And somehow you have to interpret that raw data, that's just empty blocks, into some sort of structure. So you need to give a structure for that empty space. That's what we do here. That's what inodes are. Inodes are just some sort of structure within that empty block. So it's like an abstraction over that empty block. And we also have the super block. Super block is like, at least that's how I understood it. It's like the root node for, or whatever you consider as a root node. So you have an external disk and it's just empty blocks of memory. And if you can consider the first block within that space, so it's like the first memory location, that is what you consider as a super block. And now you are actually defining something. So it's just it's an offset of one from the disk's beginning. So you are saying that if you have an empty disk and if you put the first 1024 bytes as the metadata as the super block, our file system can read it properly. So this is exactly why we have different file system names. So you might have heard of NFTS, I guess, and FAT32 and stuff like that. So these are different structuring ways. So you have an empty block and how you want to read from that block, this is what is defined by this file system standards, FAT32 and stuff like that. And based on the standard, you can read and write to this empty block, because in general that physical device does not have any structure. It's just block of memory. It's just an empty raw block of memory, just like our RAM. Even our RAM, we interpret things as blocks. If not, it's just an empty block of space. And similar to that, here we want to interpret the empty file system in some way, and we are going to use these abstractions like super blocks and inodes. And here, as you can see, if this is the high level disk layout, our first block, that is the 1024 bytes, will be considered as a super block. And super block is going to have some metadata about what are the how many bytes would you consider as a block, and what sort of types you have inside inode and stuff like that. It's just going to be a lot of metadata that you can parse to get a better understanding of how to read and write files from the system. And we have inode bitmap, inode table, and data blocks. And this is exactly what we want to fully understand. Like I wanted to tie these stuff because I don't know if this will work in my system. Because here they have actually shown, because as you know, every physical device that you have is just mapped under some dev. If you go here, everything here is some sort of physical device or some abstraction over a physical device. And let's just check df.h. As you can see, my device is of 1 TB and probably that is this. I think this. Wait. Used 15. I have to find something that's used 300 GB. Okay. Probably this is my disk. And my disk is mapped into this um, mm, and as you can see, looks like it's a different file. It says B. I don't know what is B. I know what's D is. What is, if it has a hyphen, it's just a file. Probably it's some sort of thing of macOS. But as you can see, you can open the file as just bytes, pure bytes. You don't do anything else. You move that into an image, and you read that as a pure bytes. And the first and you can actually see the first 1024 bits. So maybe it would be good if we can also try it out. Do we have the dd command? Okay, so I do have dd. Okay, so let me just try this then. We are starting from 1064 and we read one count of 496. Maybe we'll just we don't have to skip anything, so let's just read. We want to read from this disk, and output will be, should I give it as okay, test.img, and bs, let's read 1024, and we don't want to skip anything, so we don't have to put that. And how many times do we want to do this? We just want to do it once. And status, I don't know, let's just leave it like this. Operation not permitted. Maybe that's not the actual disk I wanted to. Maybe we'll try it in which disk? Well, we can try this in this. I think this is the one because this is mounted as slash. Maybe that is the one. I don't know, let's try. It still says operation not permitted. It would be so much easier if we had a just Linux system. Maybe we could just try it inside a Docker container, put a Ubuntu, pull a Ubuntu, and try it out. Yeah, let's just try it out, because I think in Linux, in my mixture, it's just a VM, so I think it should have actual kernel. My Docker is not related to my host kernel, right? Because Mac does not support this. Yeah, Mac does not support this, so I think it should work. Let's try it. Because if we can see these parts, it will be much easier to actually implement it, because probably we want to implement something like ext4. That's what I also been thinking about, because I guess this is the best file system out there. I don't know, but this is what I have seen. And in Windows, I have seen something that starts with N and FAT32 in my disk drives that I use all like really long time ago. It would always have FAT32, something like that. Okay. Okay, since we have Docker, let's just try containers. Nothing is there, so we're gonna just pull Ubuntu. Hopefully it won't use the hosts, because I don't know if let's just try docker run it ubuntu bash. Okay, do we have dd command? Yes, we have dd. And let's try ls dev df.h. And I think we could try this. Okay, and it would be, let's just copy this, paste it here, and put the VDA one. What? Okay. Oh, fuck me. What? Okay, whatever. Let's just try a tempfs then. I have no freaking clue. Being a file system, we go to inside dev. What's yum mount? Do you have anything here? Nothing. How exactly should we access a file system's real path? Because root is the slash is what is mounted into. So we have something like dev vda1 that is mounted as slash, which is the root. So maybe we won't have access to dev vda. I'm not sure. Let's just check. Read superblock of roots. See, this is the same command that we got. Do we have dump2fs? But we don't have. We do have dev vda. 2fs.h. Hatch. dev VDA1. Okay, what then let's just try SDA1. There's no such SDA here because we only have these files. Okay, whatever, then let's try overlay. Okay, then let's try list all file systems. File systems in OpenGL. It's ls bilk, and we have a lot of fucking things. We have VDA1. Then let's try VDA1. VDA. Nothing fucking works. Name. This will be the listed mounted file system because the actual file system is mounted into some name. So let's take an example of dev SDA1 is mounted as /root, probably something like that. df.t, let's try that. And we get the same fucking thing. And it's a ext4. And if we try to dump that, it does not work. Cannot find a valid super block, so it is actually trying to read the first because there is no dev, because if that's a file system it should be here. Maybe it's fucking with me. df.t. Okay, let's say Mac read super block of root in Mac. Okay, discutile list. The fuck? Huh? Let's try this then. Disk 0. Oh fuck me. Operation fucking not permanent sets. This is this entire file system is somehow does not like anything to do with us. Oh, okay, whatever. I was thinking we could do something. Maybe we can go to repel it and without examples, how can I understand a fucking thing? I guess I'll have to just go with this information. Superblock stores all overall file system layout in the disk. It starts with an offset. Fuck me. gf.g. Let's try this. We need sudo. It just says fuck you. Okay, whatever. But in general, as you can see, we need a superblock. We need to support a x44. So let's write it down. X4 support. So reads first 1024 bytes as superblock. Okay, that's at least one information. Okay. And then we can see block size information is at offset 18. So every block has a size, because you can see because this is the only thing that is static, that is the super block size, because with the first 1024 bytes is always the super block. Now we need blocks after that, but those blocks can be of any size, and that should be defined within the super block. So we need to know how much of bytes should we read as a block. So first thing we do is we read the first 1024 bytes and we store it inside a buffer. So inside buffer, store inside buffer, and then we read offset 0x18, which will give us the block size. Okay. What other information do we need? It is a log 2 value. To convert it to a decimal, we have the formula. Give us the block size. That is 2 power 10 plus size we read. Okay. And how many block counts we have? Read offset 0x4, which is block count, number of blocks. And we have block size, blocks per group. Okay, we also have groups. What is groups? Let's see. Okay, so we do have groups, and the groups can have its own blocks. Okay. Read offset 20 number of groups, read offset 0x28. There will be inodes per group, and then inode size. Okay, we do have inode size. Offset jx58, which is inode size. Blocks of size 496, and those blocks are further combined into group blocks having this many blocks, and then 400 block groups. Okay. And we can peek into the block group descriptor. Okay. How do we know the size of the group descriptor? We have the first block, that is the super block, that is of 1024. We know that we can read, and we can read the block count within that, and we can also get the block size. So the second block will always be the block group descriptor. Second block in group 0 will be the group descriptor. Let's just double check that. Can LLM figure this out? Okay. Second block in the group contains the group descriptor. Okay, it's same for xt0 and xt4. One group descriptor for each group in the file system. Inode bitmap, inode table for each group. Immediately after the second block, so that is correct. If the block size is only 1024, then the group descriptor will be in block 2. Edge case. If block size is 124, then group descriptor will be in block 2. Okay. Also, group descriptor okay. So in group 2 it will be in block Z0. Contains the full group description after the superblock. Other blocks may contain backup copies, but these are placed at beginning of their respective groups. Okay, So maybe we don't have to, in case backup is enabled, other groups will store same info in block 0. Okay. Data block bitmap. Inode bitmap, inode table, data blocks. Okay, now we know that the first block 1024 is the bytes that is needed for super block, and then if it is only 1024, then we can read the group descriptor from block 1 or block 2, depends on the size of the super block, and then we can also read the block count and group size based on different offsets. Okay, that's also fine. What else? What else? No, I guess we have the important fields. Now we have the actual block group descriptor. The table, it stores block numbers where we can find the data block bitmap, inode bitmap, and inode table. First of all, we need to know what are these three things. So this block group descriptor will have the info about block numbers. Of the block numbers, that will have the data block bitmap. Both the block numbers within a group that will have data block bitmap, inode bitmap, and inode table. And inode table. So in general, block group descriptor is just going to give us information about which block within this. So if we go here, we have block 1, that is the super block, and we have the block 0, that is the super block, and we have the block 1, which is the group descriptor, and this group descriptor is going to give us the block number that will have the data block, inode block, and table nodes, because these are blocks and those blocks has to be in some number, because only then we can look up those number, and that information will be inside this block group descriptor. Okay, and so we can use that information. What else? Various other parameters, that is just fine. Data in block descriptor can be interpreted. Okay, so we do have a data structure. within a block group descriptor, the 0th bit will be block bitmap, then inode bitmap, and inode table info, and free blocks counts. I guess we can just use this one. Absolute content. Try kernel docs. Okay, let's try kernel docs. Okay, we have this. We have the entire data structures and algorithms that are needed for this. Why the hell do we need to go anywhere else? Describe down to 10. I guess in general it will give us everything about xt4. Wait, we can do one thing. Create an image file with xt4 formats. Yeah. Yes, we could do this, and we can import that. We can use that to actually read things. We can create this. This is just wait, I guess we moved to just kernel. Okay, this is our kernel. Okay, we'll create this. It's just taking zeros into this my image and of size 1 MB and total count 1024. So I guess it will be 1024 MB. I guess that's 1 GB. So we'll create 1 GB of this, and then we can use mkxt4 of that too. Actually, we don't have mkxt4. Do we have anything? And Mac. Okay, I guess we'll have to use our Linux VM. Okay, whatever. Maybe we can create it there and then bring it back here and use that as the actual file system image for our kernel. Maybe we can do that, but let's see. Exec. What the fuck? Not exec. There's no container. There's only an image. Ubuntu. Bash. Guess we could do this here. We have created that. Now we just have to do this. And boom, our file system is ready. Let's try my image. There's no file. Fuck you. The hex dump. I guess I have to install those stuff. Hex dump. how do we put hex search hex dump? Install hex dump utils in Ubuntu. It doesn't have, you fucking moron. I don't have it. Okay, this is the one we need. Oh, fuck you. Okay, now we shall hex dump. Okay, now let's we have the image. Let's try hex dump my image. I guess my image or yum. How do I give? I guess I don't have to give that because that's too for obj dump. Okay. Oh fuck me. I don't have less. What the fuck? Okay. Sorry about that. And the first bits don't seem to match. Okay, whatever. Let's just come back to our article and see if we can hex dump it. First, let's use this part. Let's read the offset 18. My image. Block size is 0. What the fuck? That's depressing. Whatever. Let's read block count. Maybe we have to put something into it. Only then we'll be able to. In that case, have to mount. Do I have mount? How do I mount? I think I can try this. Mount image, my image to test. Okay, then test to mount image. Okay, yeah. Dev test and I'll put dev. I just created dev test. How the fuck do you mount something? Into dev. Okay, maybe we have to mount it inside Yamanti. What the fuck is a loop device? This is an image. Why not why can't I just mount it? Yeah, this is what I was thinking. Oh, only if it has partitions we'll be able to do this. We just created that image as ext64. Oh, fuck me. Why do I have to use loop? What does that loop mean? It says fuck you. Okay, fuck it. Wait, I have one more thing. I think we could just download a Debian image and mount it. I think I have that image somewhere. See the rootfs image. See, it's a ext4 file system. I prepared this image a long time ago. I don't know when. Okay, we can use this. Actually, we can just mount it here. But yeah. Mount rootfs. Add image to rootfs. What? Ext4. Oh, fuck me. Wait, I took notes. I remember it. I fucking remember it. It must be somewhere here. It's fucking here. It's inside init. Init. Nope. That is just one of the helper. Wait, let's check up then. Grab the root fs. You can see now mount the real fruit into, and then we chroot into it. I fucking remember doing it, but I don't. rootfs. Okay, in that case, let me just remove rootfs and put xt4. File image. I'm pretty sure this is my rootfs, and I'm pretty sure I mounted this image and I copied all of my code into it. See, it's here. See, I'm creating a xt4 image. I'm just moving dev0 into this, and then I'm creating mxt4. Okay, I just remembered it. I did all of this inside Linux Ubuntu machine. Okay, that's why it's fucking not working now, because it was working when I tried it, and I didn't try it in my host machine. I was trying this whole thing inside Ubuntu VM. Okay, because it's just simple as it is. You just mount the image and you give it a folder and it will work. And I just copied all the root system from this bootstrapped image into my image. That's it. And I also mounted some kernel level stuff that are needed. That's it. And I was able to create a file system, root file system. That was that simple. That's why I was like wondering why the fuck it is not working here. Okay, whatever. At least let's try if we can read from this rootfs. dd no hex dump. What the fuck was that? Hex dump. Let's just fucking copy this. Let's see how many blocks we have in that, and put rootfs image, and the block size is 0. Fuck you. How come? Okay, one last cry for help, and that would be to docker exec. No, I need to also mount some stuff. Let's just mount rootfs into rootfs. Okay, now if I try, I think I won't have hex dump there. Let's just install that fucking thing. How do I fucking install? It's here. Okay, now if we run it, G is a fucking directory. What the fuck? You're shitting me. Oh shit. Maybe. But what the fuck? But my fucking WordFS image is not a fucking directory. How the fuck does it say it's the... Okay, I'm gonna fucking give up there. I'm just gonna say that we'll just continue with this. Now we have the block number information, and we have data block, bitmap, we know that within our block group descriptor we can get the block number for inode bitmap, inode tables, and stuff like that. So if we go more, actually we could just use this. How do we read this fully? It's split into series of groups to reduce performance difficulties due to fragmentation. The block allocator tries very hard to keep each file blocks within same group, thereby reducing seek times. The size of a block group is specified by per block, though it can be calculated as into default sizes. Okay, whatever. Let's check block groups layout. Let's check the blocks first of all. Block is a group of sectors between 1 KB and 64 KB, and the number of sectors. Okay. These are totals. Yeah, this is the layout that we are looking for. The standards layout is that group 0, the first 1024, that will be the super block. Okay, so in X4, group 0 is just padding. Super block. Okay, yes, we did know that in some edge cases, if the block size is more than 24, then the group descriptor starts from 2, which is here. Okay, then maybe we'll write this as the actual thing. Mm. Okay. I have no fucking clue. I'm just trying to read through this and it's fucking boring. I guess I got colds. My fucking nose is fucking with me. Yeah. But our description was almost correct, except for this one pretty little detail that in groups in X4, the first 1000 bytes is just is padding, and block 1 and the super block starts right after that. Read the potent. But how far should we read? Maybe what we just said was correct, because even here they are trying to say that for only special cases the first 24 bits will be unused. Other than that, it should be just it should be just super block. We'll try it out and see how it works. Conform this in reality with an example. I think we will have to spawn a Ubuntu machine and test things out there, because that would be far simple, and we could actually write most of the code there and bring back things here, because the file system should just be the same and it should be scalable. It should be just scalable. Okay, that is done. I guess meta blocks and lazy blocks, we can think about it later. Now let's think about inodes. Maybe we'll read inodes here and then we'll come back there. No, we also have to think about these three things. What is a data block bitmap, inode bitmap, and inode table? Data block bitmap tracks the allocation status of data blocks within a data group. Each corresponding bit corresponds to one data block. A 0 means the block is free, 1 means... Okay, so within this bitmap, the way we have it for our memory allocator, the same thing. So every bit corresponds to a actual block, and if the block is already used, we'll have 1 here. Okay. Which constrains the maximum block group size to 8 times the block size. Why? I didn't understand. And we could just have we could just have we could just have bitmap is limited to a single block per block group. Okay, that's fine. Which constrains the maximum block group size to 8 times the size of block size. Okay. Because a block size, because this particular data block, this data block is just of 1 block size. A block data block data block bitmap is of size 1 block. So this bitmap is just of size 1 block. So that means the total number of blocks we can have will be limited to 8 times of the block size, because a single if a single block can have 8 bytes, then the total number of bits we have is 8 into 8, 64 bits. But the block can be of probably 4096, so 4096 into 8, I guess. Size. So total number of blocks within a group will be block size into 8. There's 8 bits per byte. Okay, that's fine. Now let's consider the inode bitmap. Inode bitmap records which inodes in the inode table are allocated or free. Now we have inode bitmap. That is just going to tell which inodes in inode table that are allocated. Inode in the block group. So every data block, so one data block, okay, it depends upon the size of the block, size of an inode. So every other data block can have inodes, and the inodes can be of certain size. An inode table is a contained set of blocks that store all inodes for a block group. The size is determined by the number of size of each inode. Okay. Okay, fine. Inode. Table holds the inode's metadata. Inode bitmap holds the allocated records for inodes within the inode table. Okay. I guess we know what is an data block. Data block is the number of blocks that are currently allocated, and inode table is the number of inodes that are there, and whether that inode is allocated or not is defined by the inode bitmap. Okay, it's fine. me. So every file stored in a disk is associated with an inode number. This number facilitates locating its respective inode table and the block storing the file contents. Okay, within the inode table we have to find the inodes, and that inode will give us the block that has the data. Inode numbers are from 1 to 10, which are reserved for special purposes. Okay. Inode number -1 divided by inodes per group. Okay. Yeah, this will work because if the inode number is more than inodes per group, then this number will increment. If not, it will always stay in 0. And the index within that is just the numerator or reminder, because the reminder would be the index. Because we go 1 bit at a time, so reminder would give us the index. Okay, so we also have to track this information. Group equals to inodes number -1 divided by inodes per group. And index calculation is also pretty same. You get the inode number. And how do we define a new inode number? I mean, we just take the next possible inode number that is free. Yeah. Inodes per group. Okay. This is what I want to see, but my fucking simply does not like to be seen this way. Well, let's test this one more time. We want count and we'll take it from root fs into node I Okay, now we have the root fs image. Now let's hex dump that. Okay, we do have it. Interesting. So it is a directory. Can we get ASCII? I guess it's hex editor. Do we have hex editor? No, we only have hex dump, obj dump. Okay, we have obj dump. UD. File format not fucking recognized. Okay, whatever. Hex dump. Hex dump ASCII. -C. Okay. We don't have any of such information. Okay, that's just numbers. We have to interpret them as dates. Offset 8. Offset 0. Six, 7, 8, 9. Okay. So how do we read a specific offset? Let's use this. And we need the offset 8. Okay, we have a number. We use this. We copy this and paste it here. What the fuck? Let's put date timestamp to human readable. Okay, I'll paste it here. Okay, so it is correct, because probably it was created last year. Hmm. Interesting. Okay, okay. That makes sense. Mm, so we do have some information about what sort of things that we need to access. Mm, bytes, interpretation. We don't need this. We don't need. You don't need this. We don't need this. And we don't need this. Mhm. Mm. Well, these are the things that we need. If we access those numbers, we'll get that information. Okay, that's good. What else do we need? Important portion of inode is X3 section. It's the length of from what is this? Tree section. It's length. Oh, if it's den tree, then we can actually see the value directories within an inode. Okay. If it's a directory, we can see the directories within it. I guess we still have a lot of information to collect. Only if we have all these information, then we can start implementing the support for XG4. How far does it go? And there's only few more. I still have time. Almost like actually getting the data is just for figuring out the inode number and the block, and then you just have to find how many blocks you need to read. I need an actual Ubuntu machine, and then I can try out all of this and actually implement the simple ext parser there, and then just port everything into this kernel. That way I can actually test things there. And then after once I have a good enough good enough file extent file parser, at least until the file parser, then should be good, I guess. I don't know. Yes, yes. Let's extract the inode table content from the root bar. This is what we did, and okay, this is fine. The important portions, the X3 session. I think because it's just too much theory, my fucking brain is not working. Maybe we'll build on all of this theory little by little in every session, and once we start actually writing the code, I believe it should get much better. Right now it's just theory, because in general without the theory I cannot actually implement anything, because this is just in general a parser. If you want to write a parser, you need to know the structure, because you need the structure to parse something. There's nothing else. You just need to know the good amount of structure, and then you can start writing the parser. Okay guys, I'll see you tomorrow then. I'll actually set up a Ubuntu machine tomorrow so that we can just read things faster and actually develop a simple parser there and go on about it. Okay.